steady state errors. So we looked at the transient in the last, we started looking at time response. Half of the time response is the transient, the other half is the steady state error. So, or the steady state behavior. So we looked at transient response and we looked at whether it's stable or unstable. But now let's look at this issue of steady state. So we're assuming now that the transient elements of our time function for steady state, if we want our output function from our system, well, I suppose in reality, alpha and gamma, beta and gamma shouldn't have a negative on them. We say that, you know, if these are negative, if beta and gamma are negative, then these terms are going to go to 0 over time. So what you're going to end up left with is just yt equals a, and this is our steady state. Whereas these terms, which have decayed down to 0, these ones are our transient. So the transient is very important to tell us how a system responds to a change in its input, or how it responds to a change in, say, some kind of external disturbance that comes upon it, or something along those lines. But those transients decay after X seconds, we don't know how long. And what you're left with is this steady state behavior. So why would you have steady state errors in a system? What are the physical reasons? And here are a couple listed. It could be, if it's a mechanical system, it could be due to things like static friction. If it has gears, it could be to do with things like backlash. You know, so these are some things that physically could cause the system to have an error. And we'll just have a little look at those in a minute. But steady state errors are also caused by a control system. So you could have steady state errors that result from the design of the control system. And any physical control system suffers steady state in response to certain types of inputs. Right, so we're going to go through in this lecture and understand basically, you know, depending on the type of the system, and type in this case is a very specific term, depending on the type of system which, you know, we're controlling, and depending on the type of input we have, then what's the steady state error going to be? So a system may have no steady state error to a step input, but if you apply a ramp input, it might cause the system to have a steady state error. So the nature of the response actually depends on the open loop transfer function. So let's first of all look at the classification of control systems. So control systems are classified according to their ability to follow different types of inputs: step inputs, ramp inputs, parabolic inputs. Now, in reality, you know, we've got some very nice, neat inputs here. You know, step inputs, saying, okay, you get, you know, my drawing on this thing is challenging. Go to level. Right, there we go. Took a lot of focus to do that. All right, so this is a step input. It comes in at 0 time, and then goes to, say, 1, if that's a unit step input. This would be U here. And for a ramp input, you have this a growing input over time. Right, for parabolic input, well, we haven't dealt with this one up till now, but it's pretty obvious what it is. It's going to be, you know, parabolically growing over time. So these are just ways of testing the system. In reality, real inputs are often a combination of these. So if you, for instance, giving an input, you know, as a pilot to the yoke in a cockpit of an airplane, right? What's that input going to be? is the input always going to be constant, or is it going to be always have a step, or always be a ramp? In reality, your input might be something like this as you're adjusting the yoke and changing the set point of the pitch of the aircraft, which is what that yoke does in an aircraft cockpit. Your input might look something like this. Right? So, well, I mean, what I was just trying to capture is you have sections which are ramp inputs, sections that look like step inputs, sections that look like parabolic inputs, right? Sections that have a constant input. You might come down and go negative in reality, right? So you might have a negative input where you're pulling the yoke back. So even though we use these sort of standard input types to model and to assess the behavior of a control system, the reality is that a real life control system would not really have, especially one where you're dynamically controlling the behavior of a system, it wouldn't really have those neat fixed inputs. That's not to say they're not useful. They're very useful to understand the behavior of the system, but that's not how real life inputs tend to work. You know, and we're talking here, there are sort of two types of control system if you want to broadly categorize them. One is you'd provide a control input based on a sort of varying input or a varying demand, like, you know, a yoke controlling an aircraft, the pitch of an aircraft. But you also have another big block of control systems, which would be like industrial control systems, where you want the thing to just run in a stable state forever. And the intention of a control system in that situation isn't to vary the set point very much. That doesn't tend to happen often. But what it does need to do is be able to reject disturbances as they come. So say you have a change in ambient temperature and you've got an industrial process. You want the system to be able to compensate for the change in that temperature. So it's really about, for industrial type control systems, it's about disturbance rejection. But for dynamic systems like vehicles, like aircraft, like a drone, like anything where you control an input or provide an input to a system, then all of those types are going to, you know, have this sort of varying input profile. The magnitude of the steady state error to each input is one indicator of the goodness of the system. So how much steady magnitude is how much steady state error is there to when a particular system has a step input applied, for instance. How much error is there when a particular system has a ramp input applied? How much error when it has a parabolic? So you can basically change each input, you could change the type of input and say, well, what's the steady state error to a ramp? What's the steady state error to a parabolic input? And the amount of steady state error you get indicates how good the system is, or how appropriate it is for, you know, how appropriately and effectively it performs. So this is a transfer function for a unity feedback system. I made it very generic. So as you can see, we have a gain on the top, and then we've got a series of terms on the numerator, and each term in the form of 1 plus st, and 1 plus stb, etc., all the way up to 1 plus stm. And the denominator, we have a s to the n, and then a series of 1 plus st's on the denominator as well. Each term, 1 plus st on the numerator, that corresponds to a 0 in the system. So these are zeros. So let's call this 0, 1, 0, 2, 0n. And each of the terms on the denominator, these are poles. The zeros are the roots of the numerator, roots of the denominator. The s to the n term indicates the type of the system. So that how many pure, what we call pure integrators, right? So if you have no term, if you have no s to the n, it's just missing, then effectively that's the same as s to the naught, right? Which gives us 1. So that's a type 0. So if you have none, or if n equals 0 effectively, then that gives us the type 0. If n equals, if there's a pure s, or effectively this is s to the 1, right? But just say it's an s, that will give us a type 1 because n is 1. If we have an s squared here, n equals 2, type 2, etc. Now, the number of pure integrators, or the number of s terms which you can basically take outside of your roots, your root terms of the denominator, as the type increases, then your accuracy increases. In other words, your steady state error reduces, or your system is able to perfectly track an input of different types and of higher orders. But this one I suppose we should exit because stability is compromised, so that's sort of a bad or a downside of increasing the number of pure integrators or the type of the system. All right, so we're dealing with some important conceptual stuff here. So we're going to fill out this table now. I'm going to give you different transfer functions and you're going to tell me for each one what's the type and then what's the order. So these are the 3 transfer functions we're going to look at. Remembering that order is the highest power of s in the denominator and type is the number of pure integrators. This is a summary of our results. First one here, this one has no pure integrator, so it's a type 0. But it's second order because the highest power is s squared when you multiply at the denominator. This one is a type 1 because it has 1 pure integrator. This is also, you'd recognize this as a first order type 1 system. That's what it's called when we looked at it. I think the hydraulic ram, when we added in the other factors like the loss of fluid around the edge of the ram, and when we had factored in the mass of the piston in the hydraulic ram, when we were doing mathematical modeling, we came up with this form of transfer function, and we called it a first order because this is a first order term, type 1, because it has a single s integrator here. And sure enough, it's a type 1 system, but it's actually, truly speaking, it's a second order, because when you multiply out, you get s squared here. Then this one here, the more complex looking one, the type is 2 because it has 2 pure integrators, and it's a power of 4 if you multiply it out, so it's second order. Good. So let's move on. We're going to look at steady state errors now. So let's consider a simple closed loop feedback system, and you notice there's no H term here, so there's no K term, so it's really straightforward. It's unity feedback, unity gain system. That's what we call this one. And what's our closed loop transfer function? It's always going to be forward path over, sorry, that's not open loop, forward path over 1 plus open loop, right? So the forward path is GS, our open loop is also GS. This is because it's a really straightforward, simple closed loop system. So that's what we have here. Now, if we were to take the transfer function between the error here and the input here, so say we want to get output over input, we're looking at our error as the output. So our error over our input, which is our input R, right? Well, what is it? It's not E doesn't equal R. E equals R minus our feedback. Right? So that's going to be ES equals RS minus output CS. If we then divide throughout by R to get our transfer function form, which is output over input. Okay, which is what we have here. Right? But now we know that CS over RS is G over 1 plus GS. And then what we're going to do is multiply both top and bottom right through, basically. 1 plus GS minus GS over 1 plus GS equals, these cancel, 1 over 1 plus GS. So that is our error over our input. Now this is relevant because we're looking at steady state errors, right? And it's just the same as what I have here. Okay, so we're looking at steady state errors. So now we've got an expression for our error as a function of our input. Okay. So we can multiply out and say now, okay, our error is equal to our input times that transfer function that we just derived. And if we apply the final value theorem to our transfer function, that gives us, instead of ES in Laplace, that allows us to express E at infinity, right? So what we want is, what's our error in the time domain as we go to time equals infinity? That's going to be our steady state, right? Steady state is what happens as time goes to infinity. So we want to get our error as time goes to infinity, so we can use our final value theorem to get our steady state error. So just by way of reminder, this is our final value theorem. E, we could write, instead of ESS, we could write E at infinity is this, the limit as time goes to infinity of E as a function of time. But when we looked at Laplace transforms, we learnt about this final value theorem, and we said that the time going to infinity of a time function is the same as S going to 0 of S times our equivalent transformed, or S transform, right? Laplace expression of the same term. So our Laplace expression of error ES times S, and we set the limit to 0 now. So we already have an expression here of ES, so we're going to put that in here, and that's what we have. We're setting S going to 0, that's our limit term, but we have an S, so we multiply S by this ES. Okay, so our final value theorem tells us that our steady state error, E as time goes to infinity, is going to be the limit of S going to 0, S times RS over 1 plus GS. So there are different types of RSs we might check this with. We might say, okay, well, our input RS is going to be a step, 1 upon S. We might say it's going to be a ramp, 1 upon S squared. We might say it's going to be a parabolic, 1 upon S cubed. All right, so we can apply now different types of input and say, what is our output going to be? What's our error rather going to be? Our steady state error as time goes to infinity with these different types. Parabolic, sorry, right in space, right? Different types of inputs. So let's do an example. Now in this example, we're saying that we have a conveyor belt, so we're trying to make some real life examples here. We've got a conveyor with a pneumatic lift, so things run along a conveyor, items run along the conveyor, then the lift takes those items. It could be, say, a box of parts running along a roller conveyor. It gets to a certain point, and the box has to be lifted up to the next level of conveyors at a higher elevation, a higher level. So this is a pneumatic lift in a conveyor system, and you can see the transfer function there for the plant. This is your plant here. When I say plant, that is the conveyor pneumatic lift, right? So the plant is the conveyor pneumatic lift. This is the transfer function for the plant. You also have GC, which is a controller and we're stating that GC is 0.2. This is a simple proportional gain controller, and the gain is 0.2. Assume this is subjected to a unit step input. So we're saying, okay, the boxes on our lift, okay, lift, move from lower level to higher level. Step input changes the set point. All right, so this is going to be a 1 upon S coming in here, a unit step input. So what do we have to do to determine our steady state error? What's our steady state error for this system? Well, we know our steady state error E at infinity is going to be equal to the limit as S goes to 0 of S times a mental blank here, right? S times 1 over 1 plus GS, right? So that's going to be our input. All I was missing here is putting the R, the input, because I already taken the S into account, right? So it's the limit of S times RS over 1 plus GS. Now our RS, we said, is a step that's 1 upon S. So that's going to be the limit of S going to 0 of S upon S. That's useful. You can see immediately they cancel out. Times 1 over 1 plus G S. Right. What's our GS? That's our open loop transfer function. So we're going to enter some values here. This cancels. Goes to 1. 1 over, right, 1 plus our open loop is going to be 16 times GC, which is 0.2, over S plus 0.5, S squared plus 2S plus 10. Let me just take it to one more step of simplification. S plus 0.5 times S squared plus 2S plus 10 plus 16 times 0.2. The nice thing now is because we're applying this limit as S going to 0, then once we apply that limit, this goes to 0, this goes to 0, this goes to 0. So we end up with 1 over 0.5 times 10 is 3.2. Right? And so when you multiply that out, you get a value of 0.61. Now, that's our steady state error right there. Yeah, so if we have our unit step input, our input goes from 0 to 1, then our steady state error is going to be about 0.6. So you have to subtract 0.61 is going to be our final value, which is 0.39. So the question asks us for our steady state error, and this is our steady state error, 0.61. But we could also say, well, what's our final value of our output as time goes to infinity? And the final value of the output is going to be 0.39, which is 1, the input minus the error. So let's talk now about static error constants. So this is what we call figures of merit of control systems. This is something which we could look at to determine how well or how a system behaves, how good it is, if you like. The higher the constant, the smaller the steady state error. So there are 3 actually that we use, our static error constants, and they are position, velocity, and acceleration Kp, Kv, and Ka. Right? Now, that could be a bit confusing because they don't necessarily have to correspond to a system that has position, velocity, and acceleration. They sort of represent position, velocity, and acceleration, but it doesn't have to be that the system is a position-based system or an acceleration-based system or whatever. It could be a temperature system, and in which case the Kp would correspond to your temperature value. Right? Your Kv would correspond to the rate of change of your temperature, and the Ka would be the second order rate of the position, or the first order derivative of the rate of change. Right? So it doesn't matter what your output is, and it can get even more confusing because you could have, say, a velocity-based system. So your position, your Kp, or your position error constant, then corresponds to your output, which is velocity. Right? So your position could be velocity, and then your velocity would be acceleration, and your acceleration would be impulse. Right? So that could get really confusing, but just to remember that the static position error constant, this one corresponds to the first output, if you like, that you're controlling, and the error associated with that output. The velocity, this one corresponds to the first derivative, and this acceleration is the second derivative. Alright, so let's learn what these are, and once you get them, they're pretty straightforward to use. So if you get these kind of questions, should be easy marks, because it sounds like a complex concept, but actually it's really simple in practice. So let's deal first of all with the static position, then we'll come to the static velocity, and then the static acceleration error constant. Right, so our static position error constant, remember that for a system, you know, where we're looking at if we want to get the error, we can apply this final value theorem, and so we can just apply this to get our steady state error. And then you remember what we said, that our output is equal to 1 minus our final error, assuming our input is 1. Right, so if it's a unit input, that's true. So that's how we calculate our steady state error. Now if we have a unit step input, so okay, Rs that we had in our example is 1 upon S, right? We've got a unit step input. So now steady state error, like we saw before, you're going to have an S on the numerator, S on the denominator. They conveniently cancel. So your steady state error is going to be this, 1 over 1 plus G naught. And that's actually effectively what the equation was that we used for the example we just did. Now what we're going to do is just define that our static position error constant Kp is equal to the limit of S going to 0, Gs, which is of course G naught. So effectively what we're doing is saying take Kp, and we're saying Kp equals G naught. So that means that our steady state error is 1 over 1 plus Kp. Right? So this is another way of expressing it, and you know, simply put, Kp equals G naught. What's the static position error constant for the system we looked at before? And still assuming that Gc equals 0.2. G of S, we said, is then going to be 0.2 times 16 over S plus 0.5 into S squared plus 2S plus 10, which implies Kp equals G naught equals the limit of S going to 0, of g of s equals 3.2, which is our 0.2 times 16 on the numerator, over, this goes to 0, 0, and 0. Right, so we're going to end up with 0.5 times 10 on the denominator. It's 3.2 over 5. Right, so therefore, well, we got the answer to our question. What's the static position error constant? The static position error constant is 3.2 over 5. But if we want to get then our steady state error, we learned is 1 over 1 plus kp equals 1 over 1 plus 3.2.5, and I think that's going to give us the same 5 over 8.2, yeah, so it's going to be, should be the same 0.61. So why bother with kp? Well, as we said, it's a figure of merit, or indicates how good the system is. So we know in this case our kp, is somewhat below 1. Yeah, you're going to have steady state error. If your kp got bigger, then of course, because that's features on the denominator, then your value of error is going to get smaller. Right? So if you make this kp bigger, then this is going to get smaller. How can we make kp bigger? Well, one way we could do it is, remember, this is really gc. So if we made gc bigger, if we increase this, then we increase this, and then we decrease our steady state error. So you see there's a link between our gain and our steady state error. You can see it quite simply through our kp. In fact, if you wanted to, you could actually express kp as gc times 16 upon 5. Right? So you see our kp is a direct function of our controller gain. Right? So let's look at some implications of this. So if we have a type 0 system, note the absence of an S term here. It's missing. So this is a type 0 system. Then what's kp going to be? Well, kp equals g0, which is the limit of s going to 0 of our expression here, our transfer function with all our zeros on the top and our poles on the bottom. All of these terms are going to 0, 0, 0, 0, 0, 0. All we're left with is k over 1. Lots of ones. Right? So that means that for a type 0 system, kp equals our gain k. And k in this case, actually, we should point out, this is what we call the loop gain. Because on the last example, gain gc was not, the value of kp, right? The value of kp was actually gc times 16 over 5. And so it's a proportional to our controller gain gc, but it's not actually just purely the controller gain, it's actually the loop gain. So you have to take into account implicit gains which exist in your plant and in your controller as well. Right, so you have to take the overall gain, or what's called loop gain, of this into account when we're talking about k. Now, if instead of having type 0 system, we have a type 1 system or higher, so now we've got an S term, pure integrator, then what's going to happen? Well, when you set S going to 0, this S is going to 0, with something over 0, and whenever you divide something by 0, you get infinity. So if you have a type 1, then your kp is going to be infinite. If your kp is infinite, then what's your steady state error going to be? Right, 1 over 1 plus infinity equals, well, 0. Right, so you have no steady state error if you have a type 1 system or higher, if you have a step input. So for a type 0 system, the static position error is constant, while for a type 1 or higher system, it's infinite. So let's look at a type 0 system under a step input. So our open loop transfer function is k times our plant model 1 over, or k over 1 plus st1 times 1 plus st2. Right, so if we apply a step input to this, we're going to have a finite steady state error. As our gain increases, basically our steady state error is decreasing, as you can see. Right, so for higher gains, you get reduced steady state error, but you also get this pattern here: overshoots and settling. That means that the system is relatively less stable, but you are increasing gain and you're getting lower steady state error. If we have a type 1 system now, you're seeing the type 1 come in here in the controller and on the open loop transfer function. Now, because it's a type 1 system, if you apply a step input, right, we're saying steady state error under step input, therefore Kp is going to be infinite, steady state error 1 over 1 plus Kp equals 1 over infinity equals 0, right? So as expected, our response comes up like this and settles to the set points, to the unit step input, whatever your input is, without any errors at all. If you increase k now, what you're going to do is basically still going to end up settling to the final value, to the set point, but it's going to be more oscillatory. Right, so for all gains, you've got 0 steady state error, but the issue now is we've introduced this s term here, the integral action 1 upon s. It got rid of the steady state error, but it's made the system more oscillatory. What about if you have a system with a unit ramp input? Now, this is kind of corresponds, your ramp input sort of corresponds to your static velocity error constant. So now we're not looking at the position demand or the set point demand, we're looking at what's a ramping input, a rate of change of demand. Right? And a ramp input, for a ramp input, 1 upon s squared, right? Input Rs is 1 upon s squared. That's our ramp input. So we see that turning up here, right? Because this is ESS equals limit of s going to 0 of Rs s times Rs over 1 plus G s. So now our Rs is 1 over s squared because it's a ramp. Now we're defining from here our static, well, okay, before I say that, so one of these cancels, this cancels, this squared cancels. So if we are looking at the value of s approaching 0, then you could argue that this part makes the 1 irrelevant. So we're eliminating the 1, and we're saying that the value of steady state error now is 1 over SGS, just these two terms in here. So the static velocity error constant now is, we're defining that as the limit of s going to 0 of SGS. Remember, Kp equals limit of s going to 0 just of GS, which of course gives us our G0. But now we have an S term in here, so we've added an S. So Kv is limit s going to 0 of SGS. So now our steady state error is 1 upon Kv, because this here is kV. Right. So let's look at a steady state error under a ramp input. If we have a ramp input and a type 0 system, there are no pure integrators, of course, so this is looking again at the same system we looked at earlier for a step input with no pure integrators, but now this is our open loop transfer function, no pure integrators. If this is our input, the black line, the red line is our output, and this, you can see over time it's getting further and further away from our input, so our steady state error, in other words, is infinite. It's just going to be able to, it's just going to continue to grow and grow because the system is unable to track the input. Why? Well, the steady state error is, remember, the limit of s going to 0 of s times rs over 1 plus g s. But what's happened now, as we said, rs is a ramp input, 1 upon s squared. So that implies ESS equals the limit of s going to 0 of s times 1 upon s squared times 1 upon 1 plus g s. So we cancel this s, but you still have an s on the bottom. Well, this approximates to, we said, SGS. Right, so that means because you have an s on the bottom, if s is going to 0, this term is going to 0, you're going to get infinite steady state error. Now, if you have a type 1 system, you kind of you solve that problem to a certain extent. Because now if you have a ramp input with an open loop transfer here, we end up with, if I did that same, if I just go back up, if I do this same maths, now I'm going to have a type 1 system in GS, so we're going to end up with cancelling the s squared entirely. So the system here, type 1, it has a non-zero but finite steady state error to a ramp input. So it's able to follow the ramp input, but it has a steady state error, as you can see here. I think previously I showed the error like this. Well, you could look at the error either way, really. The error in output at a certain time, or the error in time at a certain output. How long does it take to get to a certain point? So in both dimensions you have steady state error. But it's finite. It's not growing. It can actually follow the input, just not without error. Alright, so we're moving on to look at our final static error constant, which is Ka, our acceleration error constant. So Kp, that's for, or sort of is reflective of the step input. Our Kv, that speaks to a ramp input. It's the rate of change of our input. This is just a step change in our input. Ramp is rate of change input. And our Ka speaks to a parabolic input. This is a growing rate of change in our input. Right? So this is applicable for parabolic inputs, our static acceleration error constant. And if we have a finite value, that means that the system can track a parabolic input. If we have a zero value, that means it can't track at all. It's going to have an infinite error. But if we have an infinite value for Ka, then that means that the system can actually follow a parabolic input and you have zero steady state error. So now our steady state error, same equation as before, but now our Rs is this, right? 1 upon s cubed for a parabolic input. Right? So now we got one cancellation. So this becomes s squared on the bottom. So you have 1 upon s squared gs. And so we're going to define our static acceleration error constant Ka as this limit of s going to 0 of s squared gs. Right? So of course, what you have to do practically if you're calculating the Ka is you have to substitute in gs here, and then see if it cancels, if that s squared cancels out. If it does, then we can basically apply the limit value. If it doesn't, then it immediately tells us that our Ka is going to be equal to 0. So what we can say here is if, and this applies as well for all of the static error constants, if Gs is type 2 or higher, then what's going to happen, you're going to have a type 2 means that there's a sort of 2 pure integrators in our GS, and that can cancel with our S squared, right? And so then you're going to end up with a finite value of Ka, and our steady state error is 1 upon Ka. So if you have a finite value, then you have a finite value of steady state error. But if your Ka is 0, because you have GS is type 0 or type 1, that implies Ka is going to be equal to 0, because this s squared won't get cancelled. So then the s, as s goes to 0, then Ka is going to go to 0. Then Ka equals 0. If you put a 0 in here for the expression for ESS, 1 upon Ka, then that implies ESS is going to be infinite. Our steady state error is going to be infinite. In steady state error terms, Ka is given by ESS over 1 plus K. Okay, so for a unit parabolic input for type 0 or type 1 systems, you're going to get infinite steady state error. If you have a type 2 system, you're going to get a finite steady state error. If you have a type 3 system or higher, then you're going to get 0 steady state error. And that's because if you have a type 3 system, then the GS will have something over S cubed, and you're going to cancel off and end up with an S on the bottom, right? And then that S on the bottom will go to 0, and your Ka go to infinity, and therefore you have 1 upon infinity is 0. It all depends on how many pure integrators you have in your transfer function, as to what kind of response, what kind of system inputs you can actually follow. So this table summarizes it all. Starting with the type 0 system, if you have a step input, then it will have a steady state error, and that steady state error is going to be 1 upon 1 plus K. If you have a ramp input, then your steady state error is going to be infinite. You can't follow a ramp input with a type 0 system. And likewise, you can't follow an acceleration input or a parabolic input either. For a type 1 system, and your step input is going to have 0 steady state error. If you have a type 1 system, the output is going to match the input as time goes to infinity. But if you have a ramp input, it can follow it, but it won't. It'll have a constant steady state error of 1 upon K. Again, K is the loop gain of the system. If you have an acceleration or parabolic input, a type 1 system will not be able to follow it. You have an infinite error. If you have a type 2 system, then your step inputs, you're going to meet your step input. There's going to be 0 steady state error, but you could also exactly meet your ramp input. There'll be 0 steady state error for your ramp input. But your acceleration input, you're going to have the steady state error. You can follow it, but the steady state error is going to be 1 over K. This is sort of summarizes steady state error, how it works with different systems. System type is really important. when it comes to steady state error. That's the defining quality that determines steady state error. The difference between the input and the output is going to be is steady state, and it also is determined by the type of input, whether it's a step, ramp, or acceleration input. That's it for this session.